Good afternoon. I'm Bruce. Today I would like to share about Gobies VM. But before we start, I'd like to take some time to acknowledge my employer for letting me be here. I work for Zillions. We are, well, except for me, a bunch of experts in deep learning and GPU processing. We switched, or in a more fashion way, pivoted to a new direction. We are now building a smart cat feeder, which uses advanced facial recognition technology to identify your cat and track their health. So if you're a cat owner or you own by a cat, you can visit catfeed.com for more information. Now, let's get back to our topic today. Well, for those of you who don't really know about Gobies VM prior to this talk, it is a Ruby implementation. It's written in Go, and it focuses on exploiting parallelism in multi-core environment. The way it does it is by using a technology called software transactional memory, which treats operations in programming languages as database transactions. In fact, I talked about how it is done in detail in the last RubyConf. So if you are really interested and you really want to know more about it, you can always check for the video for the talk I gave last year. And so when we talk about the word evolution, I suppose most of you share the same exact idea of what evolution means, right? In fact, it usually means that something is getting better and better, or at least in our technology industry. However, when I finished the very first draft of these slides, I suddenly realized the whole talk is not really about evolution. It's not about how I made Gobies VM better. Of course, during the process, it did become better in some way. But being better is only the side effect. It's more about experiments. So let's try a little bit of this, a little bit of that, and see where we end up. The very first experiment I want to talk about is numbers. And by numbers, I mean really big numbers. When the math team used something like a programmer's best friend as Ruby's slogan, you better believe they are for real. And you can see this core idea influence the overall language design. I remember reading an interview with Matt on how he designed Ruby. And he mentioned about reducing its burdens for programmers. For example, Ruby has a dynamic typing system, so we don't have to worry about data types. Another evidence is that in Ruby, an integer has no limits. The only limit is the size of your memory storage. Until not too long ago, Gobies VM still uses built-in 64-bit integer type of Go to store numbers. It's mainly a performance issue, and of course, it did ease some burdens regarding implementations. Since I decided to perform some experiments, this seems to be a good entry point. Fortunately, Go does have its own standard library of big numbers. Well, you can see the package name, big. It surely gives you some idea. You can also see the usage below, and in my opinion, it's sort of indirect usage. Since it involves some integer manipulations, these do make things a little bit more complicated. Therefore, during my development, I bumped into some subtle bugs regarding pointer manipulations, which most of But the implementation is in fact quite straightforward and, in my opinion, very readable. So I'm not going to dig deeper on this experiment since we have a lot to discuss later. Let's just jump into what we all love, benchmarks. Well, as you can see, this tiny little snip of script is about factorial computations, which computes to 20. You might ask, why select the number 20? Because 21 will cause the 64-bit integer to overflow. That's why. And the result is like this. The graph on the left is the accumulated time of 1,000 runs. So on the graph on the right, we can see the B number version is about 11% slower than the original 64-bit integer one, which to me is kind of acceptable, because when you think about the 64-bit integer version would overflow when the factorial goes any higher than 20. Well, let's look at another example. This is a benchmark script that calculates the value of pi. I use this script to demonstrate the CPU core usage of Gobies VM before. Well, as you can see, the impact on performance in this script is not as significant as the previous one. Only 4% of performance overhead. Like I said, this is just an entry point, so it's a relatively easy experiment. The next experiment I'd like to talk about is actually hidden in these scripts. Some of you might notice the strange statement here in our pi calculation script. Well, what is this, atomic add doing right here? Well, in order to understand it, understand why we need an atomic add method or something, we need to illustrate how translation work in Gobies VM. Like I mentioned earlier, transactions in SDM are composed of bytecode instructions. When we are running these instructions inside a transaction, it's actually executing in an isolated environment to get a simulated result we want. Then the result will be validated when the VM encounters these two instruction types. One is for message sending, bytecode send, and one is for getting local variable to the stack, object to the stack, therefore bytecode get local. So if this transaction fail the validation, it will retry until it success. And if you pass, it will commit the changes done in this transaction back to the memory. Okay, before we go on, I think we already passed the threshold of not showing cats in the slides. So here's my cat. I think most of you are waiting for. And let me take a. Okay, let's move on. So with that in mind, we can now dissect this statement into transactions by step. First of all, we fetch the object from the array count using the given index 0. For the virtual machine, count is a variable name. Therefore, it is considered as getting a local variable. So, like I previously said, we will commit the translation on get local. Now, so it's committed to a stack. Then we will put the index object on the top of the stack, and we will call add method of the let specific array object. This is done by send bytecode instruction. So once again, it will be committed. Once it's committed, the VM will put the result object onto the calling stack, which here we call it count 0 ground. So the second one is about the same. So I'm not going to describe it in detail. Now, now we run across this one. It's a fixed number object. So we'll put this fixed number object on the top of the stack, which is on top of count 0 double ground. Now the operator plus will be considered as a method to call. Therefore, the message sending instruction bytecode send is issued. Therefore, it will be the result list will be committed. The change of this transaction will be committed back to memory. Finally, we call assignment method to finish this statement, which assign the later count 0 plus 1 to count 0. Well, as we did in a string-like fashion, it seems to be pretty straightforward, right? But there's a problem. In these stacks consist of transactions. The value of count 0 double ground may be outdated, but we won't even notice because it's already committed to the local thread stack. So we have no way to say, oh, it's been updated, or so we have to change its value. So when we need a statement of a block to be executed as a single transaction, we definitely need a new way to wrap these bytecode instructions together explicitly. Okay, and now this is what I have in mind. We can have an atomic block, in fact, an atomic method that runs any given block as a single transaction without committed or validating in the middle of it. The idea itself is pretty simple, so we just tag the following block as one transaction, and this transaction will be tagged as atomic. So if the transaction is atomic, it will not be validated or committed before the entire transaction has been executed. So what do you think the result will be? Well, even I don't know the answer, because last time I tried, it just keeps on running, and for 4 hours, I think. And I finally got tired and said, oh no, I need to stop this. So the reason why this is happening is that all these atomic transactions would fight to modify their shared variable simultaneously. Therefore, there would be a lot of transaction conflicts, and which cause a lot of retries. Meanwhile, no single one of these atomic transactions wants to give up trying. So these transactions are basically trapped in the retry preparatory. The other way around is to allow only one transaction to be executed. Well, in other words, it can be considered as bringing the original global virtual machine lock back where we encounter an atomic block. But to be frankly, I'm still having trouble merging that idea with the whole STM solutions, which also involves locking in many different ways. So yeah, this about it. The next experiment also regards transactions, but in a different way. Remember our example earlier to illustrate transactions? Remember I did mention about two instruction types. They trigger transaction validation and commit. Well, not only do they have impacts on atomic operations like we just saw, they also impact the transaction length and performance. Well, in the very beginning, these two instruction types are selected because they are the most common ones. For example, you can see for bytecode send is like assign 10 to A, size of an array, or just fetch something from the array. And for get local, it's just any identifier that is considered as variable that will trigger it. So the other reason is that we would like to have our memory updated after executing, for example, a method, or when we try to fetch the local variable and we want the one we fetch is the latest version, so we don't have to abort it and we don't have to retry it again. So what will happen when we allow transaction to continue executing on more than one trigger point? Now let's just bring back our old friend, the pi calculation benchmark. So this graph represents the running time of that benchmark. The x-axis down here is the trigger points threshold from 1 to 10. For example, 1 means when I encounter a single send or get local, I will commit and validate. And 2 means I need to encounter 2 of those, etc. So on this graph, you can see some dramatic performance improvement when we slightly increase the threshold to 5. However, it bounced back. The runtime did bounce back from 6 to 10. But this 6 to 10, the benchmark runtime is still better than the shorter transaction ones. For example, 1 and 2. From a transaction status point of view, however, we can see the number of failed transactions actually rises, especially for the failure during the second, the purple one, the read validation after we execute it. So, at the first glance, it seems pretty odd, right? How can a script run faster when there are more failed transactions? It doesn't make sense. So, on second thought, we must have missed something. It all becomes clear when we shift our focus to the overall, to the big picture, the overall transaction numbers. The total numbers here of transaction is dropping from 1 to 5. So we can see the most performant one. We can see the trend is actually quite like this. So we can assume this is related to the performance improvement. Although there are definitely the green ones are failed transactions, so we can see there are definitely more failed transactions. But the overall number of total transactions are dropping. So that's a good thing. Now, the other point is that longer translation, since translations are longer, if it's not aborted or not retried, longer translation actually help reducing translation initialization overhead. Now, so what experiments lie ahead of Gobies VM? Well, since I haven't finished the atomic block experiment, I think it should be on the top of the list. And as the result shows how translation lengths will have impact on performance, I think it's worth investigating on finding a dynamic algorithm which adjusts the translation lengths on the fly. Of course, I've been complaining about the performance of current parser in Gobies VM since it takes literally minutes to parse a script. With nested block, that only takes seconds to run. So this is actually the very first experiment I've done, but I failed. Well, the last one among those, last one and I think the most important one, however, is having better design documents for Gobies VM. Though I really don't consider any of you to use Gobies VM in production, I surely want to see what ideas people have in mind for a language implementation. And I also think since it's a very young project and it's relatively tiny, it's a good stepping stone for those who want to understand how a virtual machine works. Because during my development, there are times I have to do some trial and error things. And I think it's only reasonable for me to share my experiments to newcomers. Well, so that's about it. That's quite about it. So, any questions? I think we still have 3 minutes to take a few. 答疑法一通吗？
You mentioned the first experiment about finding an efficient way to have an atomic method and then run atomic operations within that. I might have missed it, but have you considered adding atomic operations to the bytes code in Gobies VM?
Well, I
mean, like a begin transaction, commit transaction, sort of like code operations.
Yeah, actually, the internal translation implementation is quite similar to what you just said, but it's in Go. So, and one thing is that the most of the method you can use in Gobies VM right now are written in native Go. So, I think there's still things we have to consider. So I think when if we try to make a native data structure, for example, a translation structure to be atomic, that will be more easier for me right now. Okay. Thanks. So, any other questions? No? Okay. Thanks for listening, and we should have a great conference. Thank you.